Hello everyone, welcome to today's webinar. My name is Neil Foley and I'm the Applications Engineer at RISE. Today I'll be discussing some best practices for creating low-cost injection molds by 3D printing thermoplastic components. So we'll first consider the two distinct manufacturing approaches involved here, injection molding and additive manufacturing. The graph on the right illustrates the typical relationship between number of parts produced and cost per part for each of these technologies. Additive manufacturing has a stable cost per unit part because the only costs associated with manufacturing a new part design are the materials and marginal costs of running the machines. Alternatively, injection molding has a high initial cost because each new part design requires new tooling, which tends to be quite expensive. However, at high volumes, injection molding can offset that initial cost with very low costs for each additional part produced. Considering these technologies together, it's clear that additive manufacturing is preferable for prototyping and other applications that involve frequent design changes or low volume production. But injection molding can be extremely effective at scaling up production, particularly if the initial tooling costs can be minimized. So this webinar will be examining how to reduce that initial tooling cost for simple molded parts by printing them with additive manufacturing and then harnessing the power of injection molding to ramp up production. Now, there is a wide variety of additive manufacturing technologies that can be used effectively to create molds. However, RISE printers and materials have a few unique features that make them particularly useful. So RISE printers use a patented technology called augmented polymer deposition, wherein we jet functional inks between layers of extruded thermoplastic. So the way this works is that first, support is extruded with our thermoplastic material. Next, release ink is placed on top of the support structure. Then the model material is extruded on top of the release ink in our thermoplastic material. And then functional inks, including marking ink, can be applied to the surface, as shown here, by jetting that blue marking ink in between the layers of the extruded thermoplastic. So Risium is our proprietary thermoplastic, and it's optimized to interface effectively with our different functional inks. And it has several features that are very helpful for use in molds. Our functional release ink, which is jetted between the interface of model and support structures, allows supports to be easily and rapidly removed, which helps get the finished part in your hand within minutes or even seconds of completing a print job. In some cases, this can enable multiple prototype iterations in a single day, allowing you to rapidly redesign and produce molds. Risium also has a very low surface energy. Consequently, most materials do not adhere well to it, allowing molded parts to easily release from its surface with no release agents or surface priming required. This makes Risium molds quick and easy to use with minimal extra processing required. Risium also has a strong chemical resistance, making it resilient to acids, alcohols, acetone, and much more, most particularly the molding solutions that we use for injection. Some other useful features include the ability to apply instructions, indicators, callouts, and other annotations using our functional marking ink capability. And finally, the chemical D-limonene, which is derived from citrus fruits and it's very safe, can be used to glue large components together. It can be used to smooth mold surfaces or seal parts for higher pressure injections. So there are just a few materials that we use with 3D printed molds. Urethane and silicone are the two primary materials that we inject. Both of these are elastomeric or flexible materials, which are useful for many applications, but will of course not be appropriate for applications that demand rigidity. In cases that do require rigidity, you can try injecting epoxies, which have had only limited testing here. So machined injection molding tooling is fairly expensive, but generally has very smooth surfaces that easily release molded parts. 3D printed molds, on the other hand, will typically have some surface imperfections that in some cases can bond with molded parts and create more friction during release. So while elastomeric materials are flexible enough to accommodate the surface imperfections typical of 3D printing and still release easily, rigid epoxies are more difficult, and it's important to smooth surfaces as much as possible and to stick to simpler geometries if you do attempt to use rigid epoxies. Now, Ryzium can be smoothed using delimonene, as mentioned previously, as well as tumbling or sandpaper. It can also be effective on more challenging molds, such as those using rigid epoxies, to separate the mold design into additional interlocking pieces, wherein each piece only touches the part on a smaller section of its surface. This will make it easier to remove individual pieces by reducing the total surface area that must be freed with each separation. Here are some of the ways that 3D printed injection molds can be leveraged. As mentioned previously, injection molding can be a powerful tool for increasing your rate of production, though this strategy will not work for all applications because, as discussed on the prior slide, the materials available for 3D printed injection molding are limited and preferably elastomeric. However, there are still many applications for which simple or elastomeric parts are useful, and the low cost of 3D printing at low volume can allow you to print several molds and linearly increase the rate of production of molded parts to a much higher volume. 3D printing and testing molds can also be a useful verification step before investing a lot of money and many weeks of lead times into having injection molds machined. Finally, some of the common uses of elastomeric molded parts include gaskets, flexible components, and soft handles, covers, or other surfaces. Now, there are several important things to consider when creating designs for your molds. First among these is the method by which you convert the design for the part you desire into the design for the mold that can produce it. Assuming that you already have a mold file for the target part, you can process that model in a few ways. One would be to extrude material around the part in your CAD software and then subtract the original part from the volume of the extrusion. This will create a perfect cavity that can then be split into your separate mold components and printed. In cases that require precise tolerances, you may find that you need to create a slightly offset surface from your part to leave extra room for the molded part to fill out its dimensions. And the final method is to use a mold making tool that is built into your CAD software. SolidWorks has this capability as well as many other CAD programs, and using it can help you make the right design choices to create an effective mold. Another important consideration is that of alignment and fastening. It's important to ensure that after the components of your mold have been printed, that they can be precisely assembled and secured such that no injected material will leak and none of the geometry will be misaligned. You can ensure proper alignment using pins or tabs to locate mold components with respect to each other. In the image shown here, there are 3 labeled locating tabs around the outer ridge of the interface, which make the rotation and alignment of the 2 pieces deterministic. When designing a mold to be secured with fasteners, make sure every segment of the interface is secured, and this may involve using many fasteners. You can see that on the mold shown in the image, there are quite a few screws that have been used to hold it together. So you can use either threaded inserts or bolt bores for this purpose. And finally, when designing the mold, you'll want to consider how the injected material will enter the cavity and how the air will exit. So you'll want to use both an inlet and an outlet hole to allow material injection to enter the inlet and allow air to leave through the outlet. So here I will discuss a few best practices when designing molds. So regarding those inlet and outlet holes, it's best to place them as far apart as possible to ensure that the injected material pushes the air out of the cavity entirely. Also, for molds with 2 or more paths from the inlet to the outlet, such as the mold shown, where half of the injected material will go clockwise and half of it will go counterclockwise. In these cases, you'll want to place both the inlet and outlet on a face of symmetry if possible, so that one side of the flowing material doesn't outrun and block off the air escape of the other. Now, to maximize the surface quality of the parts you produce, it will help to smooth the active surfaces as much as possible using delimonene, sanding, or tumbling. Any surface defects that appear on the surface of a 3D printed mold will be reflected in the surface of the molded parts it produces. So any stepping or seams must be smoothed out if you don't want them to appear on your parts. And in some cases, those things won't be a big deal, and you maybe don't need to put in the extra effort to remove them. So this is often not necessary, but if you intend to use a mold to produce a large number of molded parts, you might as well maximize the surface quality of the mold as much as possible, because it will affect the surface of every part it produces. Finally, regarding the ease of part removal, there are a few more things to consider, including draft angles, which are in fact not necessary for elastomeric parts, but which will certainly ease removal if included. Placing small indents or relief around the outside of the mold interface is useful for providing some grip or leverage to ease the initial separation of the mold components, especially if they have been both adhered to the material that was injected. Surface smoothing, as discussed, will also ease part removal. And finally, between each use of the mold, it's best to swap the surface with isopropyl alcohol in case there is any leftover material on the mold surface. I'm now going to cover a few advanced strategies for taking full advantage of molding with additive manufacturing. The first of these strategies is to create mold assemblies with more than 2 mold components. So while the simplest molds are just 2 pieces that join together on one surface, this approach is insufficient for producing more complex geometries. By allowing for additional mold components, where each component may interface with the others along a unique plane, it becomes possible to include overhangs, complex features, and perpendicular through holes, among other things. This method takes more planning and testing, but can be very powerful if this type of complex geometry is needed. Another useful strategy is to create single mold components by gluing together separately printed pieces with delimonene. This is useful when the mold component you've designed is too large for the build area and must be separated into multiple prints. When using this method, it's important to ensure that the glued pieces are perfectly aligned, and for this purpose I would recommend either that you use alignment tabs similar to those discussed previously, or use a jagged gluing interface that will make the alignment of the pieces deterministic. The next strategy is something that I've called snug feature or surface mating. What I mean by this is what's shown in the picture on the right. This is the cross-section of a mold with two components split mostly along one plane near the top. If you were to split mold components entirely along that singular plane, it is often possible that material could leak between the two components as it's injected and cover the end face of the holes you're creating. So what I've done here instead is to extrude the cylinders part of the way into the opposite surface. This creates a harder barrier for the injected material to cross and will prevent such leakage. I also created a similar raised lip around the edge, shown here at the two ends of the red circle, to prevent any material leakage out the sides. If you use this method, you'll want to be sure to draft the extrusions as shown here to avoid friction or interference from jamming the mold or preventing it from closing. And then the last advanced method I've mentioned here is the use of injector pins for epoxy molds. So because epoxy molds will be more difficult to extract, it can be useful to use a strategy from traditional injection molding and include some openings for pushing the parts out from the back. Here we'll look at a few simple use cases for injection molds made through additive manufacturing with RISE. This is an elastomeric strap that gets wrapped over two axles and creates tension between them. It uses a few snug fit interfaces, as I described on the previous slide, to prevent the two holes from being covered. This is represented by the two raised pins on the component on the right, mirrored by two indents in the component on the left. This mold also has alignment tabs around the outer edge, which ensure deterministic alignment during molding. And here is another use case. This is a soft coupling that can be used in a low torque application wherein the axles may not be perfectly aligned. Its flexibility can manage the motion and alignment of the axles, and it can also manage any vibrations that may be transferred across the joint. The mold for this part is small enough that it can be printed within one day, and it was tested over the first night after printing. On this mold, marking ink was also used to identify the inlet and outlet holes, as well as hardware callouts for fastening. All right, finally, I will quickly review what I've covered for you today. So 3D printed molds can be used to effectively accelerate production of simple parts. It also allows you to prototype mold designs for traditional manufacturing at low cost. The easiest materials to use are elastomerics, including silicone and urethane, which are useful for a variety of applications, including gaskets and soft couplings. And finally, 3D printing molds with RISE allows you to more rapidly prototype and iterate your designs, either for the molds themselves or the parts that they produce. All right, so that's all I have for today. Thank you all for attending today's webinar. If anyone has any questions, you can type them into the chat box at the bottom of the GoToMeeting window, and I'll be staying online for a few minutes to answer them. And as always, you can reach me for any further information or questions you may have at applications@rise3d.com.